Hello everyone. So let us start with the next module, that is module 5. So we'll start with the module 5 first and then come back to module 4 because module 5 is related to module 4. So if you know module 5, it's easy to solve module 4. That's why let's first start with module 5, that is matrix method. It's called as specifically called as stiffness matrix method. Okay. So and this method is also known as stiffness method, equilibrium method, or displacement method. Okay, so the steps are similar like what you have done before. So let us solve this using a problem directly. Why it is called stiffness is because we are using the concept of stiffness, that is K. We are using stiffness, that is K, which we have used earlier, and we're using the equation, that is stiffness equation. Here we'll be using the stiffness equation for this, that is K into delta is equal to P minus PL. Okay, this is the stiffness equation. We'll be using this equation and using it in the matrix to solve the unknowns. Okay, so let us take an example. Okay, so analyze the continuous beam by displacement method. So in exam they might ask you like displacement method or stiffness method or equilibrium method. All three mean the same. All right. Okay. So in the given problem, you can see here there is a fixed beam at A, and B and C have hinge support. Okay, and there is a load at there's a UDL of 60 kilonewton in between AB, and in BC there is a point load of 100 kilonewton. Okay, all right. So the steps goes like this. So before you could start with the fixed end moments, first we have to find out the kinematic indeterminacy. So we have already studied what is static indeterminacy and kinematic indeterminacy. So kinematic indeterminacy is nothing but the basic unknowns. Okay, these are the unknowns which you're going to find here. Uh, that is the rotations, okay, and displacements. So you can see here. Okay, first it goes with the formula. So if you want to find the kinematic indeterminacy, so it is 3j minus r plus m. So 3 joints are 3, A, B and C. So 3 joints. So 3 into 3 minus reaction. Okay, so draw the reactions here only, immediately below this. That is at A it is a fixed support, so 3 reactions. At B hinge, 1 reaction. C also hinge, 1 more reactions. So total reaction is 5. Okay, then members, that is 1 and 2. Okay, so then solve this. So 3 into 3 9 minus 7. So kinematic indeterminacy is 2. So the meaning of this is, in two uh, joints, the kinematic indeterminacy is 2. The meaning of this is, at two supports there will exist the kinematic indeterminacy. That means there will be two unknowns. Okay, now how to determine this is, first just draw this diagram first. Just show the beam, that is A, B and C. Then uh, then check out with these two diagrams. Okay, so this is a fixed support. Reactions are already 3. Okay, so it cannot move in vertical direction, horizontal direction, and there is no rotation happening. So there is no rotation at all happening here. It cannot rotate in this joint. Now come to joint B. So in joint B, you can notice there is a reaction here. Okay, there is a vertical reaction. So reaction means it cannot move in that particular direction. Now that it cannot move in that particular direction, so it can move in the second direction. So because it is a hinge support, the horizontal force, that is the horizontal reaction, is neglected. So because it is neglected, so the third degree of freedom would obviously be the rotation. So the 3 degrees of freedom are, first is horizontal movement, vertical movement, and the rotation. Okay, so here also the reaction is happening here. Okay, so reaction means it is stopping a vertical movement. Then horizontal movement is neglected, so it can move in the third direction, that is it can only rotate. So that would be first unknown. Okay, that would be first unknown. Similarly, in the C direction, okay, in C you can notice here, in again same thing, there is a reaction here, the reaction is happening here, so the reaction is restrained here, so it can move only in the second direction, that is, see, okay, so the horizontal movement is restricted and it can move only in the third direction, that is rotation. So kinematic indeterminacy, so you have to show it here only, that is 1 and 2, okay, so it can move only in here, B and C. All right, so okay, so after this, find the fixed end moments. Draw this diagram immediately below this, then find the fixed end moment. So before we start with fixed end moments, there is draw the diagram. That means whenever you're finding the fixed end moments, we are going to consider uh, all the supports as fixed supports. So show here A, B also fixed, C also fixed. Okay, then find the fixed end support, fixed end moments. That is MFAB, and then it is again UDL, so it is WL square by 12, BA plus WL square by 12. MFBC is WL by 8 and MFCB is plus WL by 8. Find the fixed end moments. Okay. Main important thing is finding this kinematic indeterminacy and showing here. Okay. And it's very important you mark this here, that is 1 and 2. Okay. We'll be using this further. Okay. So now next, the forces developed in the coordinate direction due to the loads are, now there are two loads acting here. Okay. So we'll be considering this now, coordinate direction 1 and 2. Okay. So B is connected to A also, C also. So so B will write it as, so PL. So it is right, P load in coordinate direction 1. Hmm? This is first load. So first load, that is load in coordinate direction 1. So B, it is connected to BA also, BC also. Okay, so it is like MBA plus MBC. So we have already calculated this MBA, MBC. Okay, then right, P1L. Okay, next, similarly P2L. 2 means in the second coordinate direction. So load in BC is how much? This load. Okay, so MBC. So MCB is 37.5. Okay, all right. Once you calculate this P1L, 2L, then we'll be using it in the formula later. Okay, now the above forces are positive if they act in the positive direction of the coordinate. Okay, so both are acting downward like this. They both are acting downward, and both of them give a positive moment. Okay, all right. So next, now this is very important, understanding the stiffness matrix. Okay, so we are going to use the slope deflection equations and formulate the stiffness matrix. Okay, now how to find out this is, so first write stiffness matrix, then draw the diagram. So now see here A, B and C. All right, now coordinate direction, first draw the diagram like this and show all the supports are fixed, A, B and C. All right, now in then draw the show the rotation. So what we're doing here is, 1 radian rotation is given to supplement. Okay, so see here, 1 radian means theta is equal to 1 radian, which is given to support B in coordinate direction 1. So where, so this is the first direction for us. So see here 1 and 2. So whatever we do, we start with 1 and end with 2. So I'm making some corrections. I'm going to add loads and rotations at B first. Then after that, I'm going to again do the same process for C. So because this is the first coordinate direction at B, so it would be, okay, now see here, always I'll apply a rotation which is clockwise. So that's why I'm going to draw it like this. See here, show it clockwise first like this. Okay, then write theta is equal to 1. That means theta is equal to 1 radian. Now, after this, when I apply 1 radian here, so you can see here, what happens? This theta would try to push the beam upward here. Okay, BA goes upward, all right, then BC goes downward to keep it in equilibrium. Okay, so see here, this, that means when I apply rotation at B, so BC is going to bend downward and BA is going to bend upward. All right, so show this diagram like this. So this is the deflected shape of the beam because the radian, that is theta 1, is applied. All right, okay. After this, once you, so the first step is show theta is equal to 1 radian at B. Next is show the deformed shape of the beam due to this theta 1 radian. All right, theta is equal to 1 radian. Okay, next you need to show this. This is very, very important. See here, K means it is stiffness. Stiffness. So write this as K1, means it is in the first coordinate, first direction. Okay, here it is in K2. K2 means it is the second coordinate direction. Okay, so first write K1, K1, K2. Just write it like this. Then the next suffix, that is the next number, would indicate the coordinate, like in B, that is in first direction you have applied the unit load. That's why that represents 1. Same thing, effect of 1 at 2. That means, okay, once again I'll repeat this. As here you have added, first you have added 1 kilonewton, 1 degree, that is 1 radian, that is theta is equal to 1. Now first write K1. K, okay, theta is nothing but rotation, K is nothing but the displacement. Okay, so K1, K2, because it's the first direction, B is the first direction, so 1, and K2 would be the second point. All right, next K11 means you're doing something at A, you're applying a load at A, that's why this will indicate 1 1. Similarly, K2 means because you've applied a load at 1, the effect in 2 represents K21. Okay, all right, so once you write this, okay, once you write this, next is you have to find out this. Now see here, K11 means it is connecting BA also, BC also. So for this we are going to use the slope deflection equation to find, that is, see here, K11 is equal to 2EI by L. Okay, use a formula 2EI by L. Then theta, first B to A, so first joint is B. So because our first joint is B, so that joint should be multiplied with 2. Okay, so it is like theta A plus 2 times theta B minus, okay, delta. Delta again 3 delta by L. So you can just write it as 0. Similarly, next again B is connected to BC also. So because it is connected to BC, so again 2EI by L. Then from B to C, okay, you have applied rotation, you have applied a moment at B. Again, this is the first point. Because it's the first point, so it is 2 times theta B plus theta C minus 0. Okay, then you have to just solve this. Okay, solve this, then you'll get see here again theta A and theta C are the fixed supports. Okay, again whenever you're writing this, only at which joint you're applying the rotation, that is the theta, only that joint should be released, other joints should be fixed. All right, that's what we have done here. Other joints are fixed, that is theta is 0, theta C is 0. Next, so we got solve this, then we got K11. Okay, so I've written here 7 by 3. You can always solve this and keep it in terms of decimal, because decimal, in decimal if you keep it becomes easy when you're solving the matrix. Okay, all right, so directly we'll be solving this in the calci, the matrix. Okay, so this is 7 by 3, that would be 2.33, I guess. All right, next is similarly find this unknown here, K21. So K21 is again saying 2EI by L in this direction. Then so 21 means CB you have to write. So CB means the first joint is C, so it is theta B plus 2 times theta C is equal to 0. Again theta C is a fixed support, so it is 0. So it is now 2 EI by 3. Okay, solve this. You can solve this and keep. So these are the unknowns. Next, Similarly, the same process should be applied at joint C. So when you're applying at joint C, again same process, that is unit displacement in coordinate direction 2. Now again, if you add a unit rotation at 2, what would be the displacements happening? Okay, now see here, again A, B, C, draw it as it is, only in coordinate direction 2, that is at C, that joint you have to release. You have to release that joint and apply the load. Okay, so fix A and B. All right, so now at C, the first thing is apply the uh, theta is equal to 1 radian at C, that is in coordinate direction 2. So because you have applied in here, that is at C, what happens when this rotation, again the rotation should always be clockwise. Because it is clockwise, see what happens when it goes like this, it tries to push again CB upward. Okay, so show this deflected shape of CB. So once you show this deflected shape of CB, again see here AB is not affected only, because whatever changes you have made, whatever moment you have applied, it is only at CB. All right, so only CB is affected. So because of this, all right, so only just draw this, only CB goes on top, deflected shape. Okay, then the next thing is uh, you have to show the rotations. Okay, now what's happening here at C and B, both are rotating. All right, so now see here, again this is a clockwise displacement. Now see here, K1, write it as, because the first coordinate direction, write K1, the second coordinate direction K2. All right, next, the impact is happening at 1 and 2 because of you have done something at 2. You have added theta is equal to 1 at 2. That's why we're going to write the next suffix number, that is 2 and 2. Okay, so always remember the first place indicates the coordinate direction. So K1, K2, that will be fixed. Next, because you're applying rotations at 2, so this would have 2 and 2. Okay, all right, so once you've formulated this, draw this diagram. Okay, next is K12. Find out K12 is equal to, again it is connected, K12, only this portion you have to take, that is 2EI, only BC, because AB is not affected, right? So BC only, so 2EI by L, then 2 times theta B plus theta C minus 0. All right, next, similarly K22, that is theta CB. That means MCB, that is 2EI by L theta B. Okay, theta B, only C is affected, right? So first term, that is 2 times theta C minus delta, that is 3I delta, 3 delta by L, that is nothing but 0 here. Okay, then again this things also, I have kept it in fractions, you can always keep it in decimals. It's better to keep it in decimals. All right, next, the final forces acting in coordinate direction 1 and 2 are 0. Okay, so the meaning of this is, in the given problem, okay, all the forces here, they're all linear forces. In the given problem, there are no moments acting. Though there are no moments acting. In case if there were extra additional moments here, okay, extra additional moments here, then you would have considered that. In this case, it is a simple problem, so we're not going to consider any moments. So it would be P is equal to, in coordinate direction 1, there are no moments, 1 and 2, there are no external moments acting, so this would be 0. All right, okay, now we'll be writing the stiffness matrix. Okay, so stiffness matrix is given by K into delta is equal to P minus PL. Okay, so stiffness matrix is given by K into delta P minus PL. So K is nothing but, okay, you have to write this in the matrix form, whatever I found. Okay, now writing this is very important. Now see here, K11. Okay, so K11 is the first row, right? Next, second row, always these number indicate, the first number here indicate the rows, and the second number indicates the, this here, column. K1 means it is the first row. First row, first number. K12, that is first row, second number. Like this. 1 means you have to write in terms of rows. Next, K21, K22. So 1, 1, 1 should be in the first column like this. 2, 2, 2, second column. Okay. All right. Next, delta 1, delta 2. Here two deltas are there. Deltas are nothing but the unknowns here. All right. Next, equal to P. P is there are no external moments acting. So P would be 0. So 0 and 0. Then minus PL. PL means two different direction. So P1L, P2L. Okay. All right. So next we have to write this K11, whatever we found out here. K11, 7 by 3, 2 by 3, then 2 by 3, 4 by 3. You have to write here carefully. If you write this properly, then next is just the substitution. Then delta 1, delta 2 equal to, okay, 1 P1L. We have already calculated here previously. So it is again minus. Here it is plus, but according to formula, it is 0 minus P1L, 0 minus P2L. Okay. All right. So once you write this, 42.5 minus 37.5. Okay. Next is, I have used a manual method here to solve this. That I've taken a common, that is EI by 3, then put it in the matrix, then delta 1, delta 2. But there is another simplest method to solve this. That is, we'll be doing it in the calci directly. I'll tell you the step-by-step procedure how to do it in the calci. So I'll be using this FX991 MS calci to solve this. Okay, so keep it in the form first. Keep it in form of delta. So delta 1, delta 2, delta 1, delta 2. Then here, this portion goes here. So inverse. So we'll be writing it as inverse matrix. So delta 1, delta 2. So this becomes, when it goes here, it becomes inverse. And 42 minus 37. All right. So here I've used a manual method. Okay, I'll tell you another simplest method to use this. Okay, first keep it in this form. Okay, so solve this and keep. That is 7 by 3 is 2.33, 2 by 3 is 0.67, again 2 by 3 is 0.67, and next 4 by 3 would be 1.33. All right. Okay, so now take the calci and press mode 1, 2, 3, 3 times. Press mode 3 times. Then you'll get equation mat and VCT. Okay, there you have to choose mat. Okay, it's a matrix mat. Okay, then now you're in the matrix mode. All right, then press shift mat, that is shift number 4. Okay, shift number 4 will give you mat. Okay, in this you have this option dim, edit, mat. Okay, so dim, you have to first choose dim, means it's the dimensions. So press 1. So again it will ask A, B, C. So first is this will be treating like matrix A, and this is matrix B. Okay, so matrix A, choose 1. So it will ask mat A, M into M, M into N. So first M means row, N means column. So here 2 rows, 2 columns. Okay, so press mat A, M is 2 and N is 2. Okay, so now you have to, again it will ask mat A 1, 1. That means you have to put this value first. 7 by 3 is 2.33. Okay, next mat A12 is 0.67, that is 2 by 3. Next, again it will ask this number 0.67, and then this last one is 1.33. Okay, so we have done with, we have entered matrix A. Okay, we have entered matrix A. Then again press shift 4, that is mat. Then again press dim, that is dimension. So we'll take matrix B now. So this is matrix B. So matrix B is 2. Okay, so in 2 it is again 2 rows, 1 column. So M is 2, N is 1. Okay, so again it will ask mat B11. So this is minus 42.5. Then this is minus 37.5. Okay, so I've entered. Now both the matrix are fed in the calci. Okay, they're in the memory. Now what you have to do is again press shift 4. Okay, that is again the matrix. Okay, then you have the third option mat. Press mat. Now again it will ask A, B, C and answer. So press 1, that is mat A. So it took mat A. Now this is mat A is in the calci now. In raised to -1. So it is inverse 1. Again used in the calci. Okay. Then into, press into this one. Okay. That is again shift mat. Okay. That is shift number 4. Again go to matrix, third option, and choose B. So it is like mat A inverse, mat B. You can read it in the calci. Okay, then press equal to. Okay, so when you press equal to, again, no need to do all of these calculations, because right now it is just 2 by 2. It's easy to solve. But when the number becomes more, then it's very hectic. So it's always better to solve it in the calci. All right. So we have got the answer here. The first one is 1 by EI. So it is 11.84. I've solved it in the calci. It's 11.84. And the second one, just press the next arrow. So you'll get 22.22. Okay, I've got both of these in the calci directly. So theta A, theta B would be the first number. Okay, because it's a coordinate direction 1, theta C is coordinate direction 2. Theta is obviously 0 because it's a fixed support. Okay. All right. So again, to check out, to solve this, you can just rewind the video and just watch how to solve it. All right. Okay. Next is, once you find out this unknowns, that is theta A, B and C. Next is again same thing what you have done, solving slope deflection equation. So MAB is fixed end moments. Okay, so MAB is fixed end moments plus 2EI by L. So 2 times theta A plus theta B. Okay, minus 3 delta by L. Again it is 0, so no need to write also. Alright, so you can just put this fixed end moments. Same thing what you have done using slope deflection equation. Theta is 0, only substitute the value of theta B. Similarly, MBA, same thing. Say apply the formula, fixed end moments, again 2EI by L, same formula, slope deflection equation. Then similarly, MBC, fixed end moments plus 2EI by L. So B is the first term, so 2 times theta B plus theta C. Substitute all the values. Then MCB is again fixed end moments plus 2EI by L. Okay, and the check is here because in the starting we had seen here C is a simply support, right? C is a simply support. So at C, the moment would be 0. That's why we have got here 0. MCB is 0. And the check is MBA should be equal and opposite to that of BC. If this is plus, this should be minus, and vice versa. So if you get this answer right, then what you have done is right. All right. Okay. So with this, we'll end the problem. That's all for today. Thank you.